last time, so what did I do last time? So, oops. So last time we considered dj equals d on dxj, and we saw on Rn, or on omega, which is a bounded domain, so say smooth domain. And we saw that the weak derivative that we're used to, so okay, we also saw that the formal adjoint, I mean this is just integration by parts, the formal adjoint is the negative of dj, so dj formal adjoint is negative dj, and we saw that the weak derivative is actually equal to just the adjoint, the L2 adjoint of the formal of the formal adjoint. Okay, so this is a dagger. Okay, so we want to take this perspective now, this operator theoretic perspective, to start talking about boundary value problems, and for that understanding maximal and minimal extensions. So maximal and minimal extensions. Okay, so let's define some. So let me define the operator d subscript c to be exactly the operator d, but with domain, or maybe it's maybe I'll call it dcc actually, with domain dcc equals to c infinity cc of m landing us in E, and dcc dagger, formal adjoint to be, so here I just mean that it acts exactly as d or d dagger with now domain dcc dagger equal to c infinity cc m landing us in F. Okay, so in this language we saw, so recall that, so what do we have? We have that dcc of uv, and this is L2 of m in F, is equal to u dcc dagger v in L2 of me, right? And so this is, of course, for all u in the domain of dcc, which is of course equal to c infinity cc of me. Sorry. And for all v in dom dcc dagger, which is of course, I mean, I'm just writing this thing out just to really emphasize. So we have this adjoint formula. So just like before, I mean, here we had the formal adjoint being the negative dj star, and the weak derivative we formulate, I mean, we saw that it's the adjoint of the formal adjoint, right? So motivated by that, I mean, it's really the only thing we could do. We define the maximal operator, dmax, as equal to dcc dagger star. So okay, I should write here define, right? So this is really a definition now. So define and d max dagger is equal to d cc L2 adjoint, right? So this is the definition we make. So, okay. So what is now the domain? So let's just consider what the domain of D max is, right? So let's just be really explicit and write this out. So what is the domain of D max? So the domain of D max is going to be the U in L2 ME such that there exists some W in L2. I mean, this is really the analog of the weak derivative, okay, in MF, such that the following formula holds, right? So U in DCC. Sorry. So the question is the D max dagger the formal adjoint of the D max? No. It is not. If the D max dagger was the formal adjoint of the D max, then we wouldn't really have anything to do. Okay? And remember, formal adjoint, so let me just make a remark here. Formal adjoint really means on compactly supported smooth sections. It is not on, you know, the domain for the formal adjoint, that language is fixed to mean that it is really an operator that is defined on compactly supported smooth sections. I think the question is, maybe the refined question is D max the adjoint of D max perp? And absolutely not. Right? That's, in general, that cannot be the case. Okay. And we'll see that if it were, then we wouldn't have any boundary value problems. So anyway, so the domain of D max, so these are the U in L2 such that there exists W in L2MF such that this formula holds, right? WV. So this is what it means for something to be in the domain of D max. So we can understand this again in a slightly different way. So we have the Rees representation theorem to play with, right, in L2. So this is from the Rees representation theorem, what I'm about to write. So this is exactly the U in L2 ME such that the map V mapping to, so V maps to UD formal adjoint V is continuous in L2 of MF. Okay, so this is really a functional now. So we're saying it's a functional in L2MF. So again, we have an equality here. We can characterize this in a slightly different way. So this is the L2 sections such that there exists some constant, possibly depending on the U, and certainly depending on, say, D bar, or, well, D bar is determined by D, say, such that UDCC dagger is bounded against this C, against the L2 norm of V, right? And this is for all V in C infinity CC of MF. Okay, so actually I should really say, so for so these v's for which we're considering is again C infinity CC of MF. And of course, C infinity CC MF is a dense subspace of L2. We've already seen that. So such a map which is continuous is going to extend continuously to all of L2, right? So there's a unique extension. But this is another way of phrasing it. So we can really concretely understand what the domain of Dmax is. So clearly what we have is the following. So clearly, as operators, we have DCC is contained in Dmax, and DCC is contained in Dmax dagger. Okay? So what do we mean? So let's just recall what we mean by this. So let's just be really careful here, because maybe you're not so familiar with moving between thinking in terms of operators and Banach spaces, so or norm spaces. So we have so this is really saying that we're looking at DOM DCC as a subspace of L2, and this is of course contained in DOM Dmax. All right, recall that this is what it means, right? And similarly for DCC perp. So we have an operator that is contained in a larger operator, right? In the graph norm. This is true in the graph norm, right? So we want to really, we're not just considering this as an L2 subspace, we're really considering this as a Banach space with respect to the graph norm. And we have an operator contained in there, and it means that this operator is now closable. If I take the closure of this operator, then it's going to still be contained in DOM Dmax, because DOM Dmax is closed in the graph norm, and therefore it's going to give us an operator, right? So then I can define, so let me maybe just write that. So DCC in Dmax means that the graph of DCC is contained in the graph of Dmax. Therefore, graph of DCC closure is also contained in the graph of Dmax, right? Remember, the adjoint is always a closed operator, right? So Dmax and Dmax formal adjoint are closed operators. So since the adjoint is always closed, a closed operator. Okay. So this means that we have some operator such that G of DCC, so it means that DCC is closable, right? So this is equal to DCC closure, i.e. DCC is closable. So then we can define D min as the closure of DCC, and D min dagger is the closure of DCC dagger. Okay? So in relation to the question that was just asked before, what is true is the following. And I'll just leave it as an exercise, that D min L2 adjoint is exactly equal to D max dagger, and D dagger max, D dagger max adjoint is equal to d min. Okay, so this is the relations that you have of the adjoints. So d min and similarly you can say the same thing for the other pair of operators also, right? With the dagger and the non-dagger operators replacing the dagger and the non-dagger operators. So what this is really saying is that so d min and d max dagger are, hang on, have I written this right? Let me just see. D min star. Yes. So it's really the adjoint of d min is d dagger max, right? That's really the statement that's true. But d max and d max dagger will not be adjoint to each other. Okay. In general. Okay. So now let me just talk about what a typical PDE formulation is, just to motivate what we're going to do. So a typical PDE formulation so we have some M, we have some interior pointing vector field T, well, I'll just call it T without the, and typically we want to do something like this. We want to say du is equal to F, so we want to solve. So we want to solve du equals F, and the partial derivative in the T direction of order K of U restricted to the boundary we want to prescribe, right? We want this to be equal to some fk, and this is for k equals to 0, 1, up to m minus 1. I mean, conceptually, if we had up to order m, it would be over-constrained problem. So the fk's here, so these fk's are, you know, measurable sections of some sort. Typically maybe it'll be smooth, but these are at least measurable sections on the boundary, landing us in E. Okay, so this is a typical PDE formulation, and unfortunately, even the way that I learned PDE, you know, one sort of sees just this, and this is what we really talk about in terms of boundary value problems. But actually, it's really important to separate two very important aspects of this problem into two very separate parts. Okay, so the first part, so we really need to separate these two aspects for a systematic treatment. So two aspects for systematic treatment of BVPs. So the first aspect is, where do the FK live? So to really think about this systematically, what we desire is some function space B that of sections living on the boundary, right? So here I'm just denoting it to say that it's some function space of some sections on the boundary, right? So this is of measurable sections on the, well, maybe move this here. So these are measurable sections on the boundary. Okay, so this is some function space. And so what we wanted to do, so maybe I'll call this B equals this. And here's just to note that there are sections on the boundary. So what we wanted to do, we wanted to induce an extension dB with the extension now sitting between dmin and dmax. Right, so once we understand where the fk live, what we wanted to do is to give us an operator. Okay, when I say give us an operator, I want a domain, right? So what do I mean by this exactly? So this is to say that the domain of the dB are exactly the u in the domain of dmax, such that tk of u restricted to the boundary is exactly landing us in B. Okay, this is what I mean when I say that it's sitting between dmin and dmax. Okay. So what are boundary conditions? So this is what we call a boundary condition, right? So B is a boundary condition. Okay, so this is just really informally speaking. So what we want then is to really travel between domains of operators and boundary conditions, right? In what is to come, these two things are going to be synonymous. I want to have information on the boundary that gives me an operator, extension of the operator on the interior, and I want to be able to move between these two things synonymously. Okay, so i.e. B is in correspondence with DOM DB, right? And I wanted to be able to go back and forth, right? Or I should maybe say DB, right? Which is of course just specifying a domain for this operator. So this is the boundary condition part, okay? So boundary value part. And the second part is the problem part. And in this lecture course, I'm not really going to worry about this second part, right? So for which B can we invert dB, right? So if we can somehow invert this operator, then it means we can solve the problem, right, that we're given. So I should, for which B, and I should say for which F. Okay, so for which B boundary conditions, or boundary condition, and for which F in L2, so that might again be some subspace. Okay, so now the F are some sort of a subspace in L2. Maybe living in subspace F in, well, say F. Can we invert dB? Okay, so the second aspect, I'm really gonna not worry about it. Okay, that's not really something that is very much of a concern for us. But the king of it all is really to first understand the boundary conditions. Okay, solvability of PDE is a secondary question. Without really a systematic approach, in the past, in the early days of really PDEs, people would just fix a certain boundary condition and mix the two together. And we'll see as the course goes on how we can think about things like Neumann and Dirichlet boundary conditions for the Laplacian in terms of this language. But the really important thing is to be, so the goal here is to understand not just one or two boundary conditions, but really to understand all boundary conditions, okay? So everything lives in DOM D max, Okay, so I really want to emphasize that point. So, so now I want to formalize this one, right? So formalize this first point. So what do we need to do to formalize it? So to formalize it, we need to pull the interior operator, i.e. Dmax, or the interior operators, i.e. dmin, dmax. The min is also important. So the pair of operators to the boundary. Right? We need to somehow have a way of pulling this entire problem. So everything we want to know about the domains of dmin and dmax, we want to pull everything to the boundary, right? That's the first thing we need to do. It's sort of like if you want to fix, I don't know, if you want to fix something, you might have to dismantle it first and put it on a table and then pull it apart, right? So this is sort of what we're doing now. We have these operators that we want to understand on the interior, but we want all that information somehow to be pulled to the boundary, okay? So, yes? Well, I mean, they see the interior. So the question is, why are they interior operators? Well, I mean, there are different ways of really trying to approach this. Of course, we are now looking at manifolds with boundary. But if we didn't include the boundary and we just looked at the interior operator, we can still just make sense of dmax and dmin for sections just only sitting in the interior. And actually, these extensions would correspond exactly to the extensions that we've defined where we include the boundary in the space. So maybe that's an important point to make, because if your boundary is sufficiently low regularity, you may want to proceed considering boundary value problems without including the low regularity boundary into the manifold itself, because then you have to now start dealing with non-smooth manifolds, right? So there you exclude the boundary and you consider that a separate piece, and on the interior you have a smooth manifold with boundary, and then you're just trying to understand the problem on L2 of the interior of M, right? You could do that here too, actually. We'll see an example of that in a minute, okay? So let me just say, when I talk about interior operators, I mean the operator that sees the interior. Of course, in the way that we've done it, the operator in some sense also sees the boundary, but we want only the boundary condition to govern the way in which it sees the boundary, okay? So let me just say what I mean by this. So what I mean by this here is that, so recall that, so I mean we have that dmin is contained in dmax by construction. So I mean, and these are both closed operators, right? So this is equivalently, we can look at dom either dmin or max with respect to the induced operator norm. So this is a Banach space. Okay, so this is a very important point that I really want to emphasize. So these are Banach spaces. So thinking about extensions, so looking at trying to understand all possible extensions, not necessarily closed, right? But all possible extensions here. So dx possibly non-closed, right? Need not be a closed operator, but the point is that this is going to correspond to subspaces. Dom dmin, so that's a subspace, and then we're going to have some subspace here, say x ext. Of course, this is the domain of the operator, right? So I'm just writing x here just to say that it is a subspace. So if we have such a subspace, it's going to give us an operator, right? Because it's contained, the subspace is contained in dom dmax, and that's really the point. Okay, so this is going to correspond back and forth. So let's just leave the world of operators for the moment and just think about this abstractly, right? Let's just think about this problem abstractly first, just to get a handle on this. So abstractly, what we have is this: we have B1, B2 Banach spaces. And I want gamma to be bounded surjection from B1 to B2 with B0 being the kernel of gamma. Okay, that's the abstract setup for the moment. So I want to make the following claim. Proposition. Gamma induces a Banach space isomorphism gamma tilde B1 mod out B0 to B2. If I have now a subspace S sitting between B0 and B1, so it is a subspace possibly closed, and that means that gamma S is so if S is closed, then gamma S is closed, right? Now, if S is a closed subspace, possibly closed, then the inverse image of S is a closed subspace satisfying B0 gamma inverse S B1. Okay, and the last point I want to make, and this is an important point, is that S is equal to gamma inverse gamma of S. Okay. All right. Okay. So the reasons for this will become clear in a second. Why we want to do this, right? So, okay, maybe I should give the example first, and then I should give the example first, and then move on to the proof. So what we want, so what we're thinking of is B0 being the minimal extension, B1 being the maximal extension, and B2 being some space on the boundary. Okay? So, okay, actually, let me give the example after I give the proof. Yeah, let me do that, because the example is not going to really give us some information on the boundary, but it's going to give us another piece of information that's important later on when we talk about the boundary. Okay, so let me prove this first. Okay, so point number one. So the induced gamma from B1 to B0 acting on B2. So how does this look? So this gamma of U plus some b naught in the quotient map is just equal to gamma of u. Right? That's the action of the induced map. So, okay, so now what is the norm on this space, right? So we have u plus b naught in this quotient space. So this is exactly equal to the infimum over the u plus b naught, such that b1, such that b naught is in big B naught, right? Little b naught. Okay. So, so gamma of u, this is going to be the same thing if I write gamma of u plus some b naught, because the b naught is in the kernel, right, of gamma. Remember, this space, capital B naught, is the kernel of the gamma. And obviously, this is a bounded surjection, so this is going to be bounded against some constant as follows. Okay? So what this tells us is that gamma tilde of u plus b naught this is in B2, is now bounded against u plus b naught in this quotient space. This gives us that this is a bounded map. Okay? So we have a bounded map between a bounded surjection, in fact, between, because remember, the gamma was a surjection, so of course this is also a surjection, right? We've just modded out the kernel. So this is a bounded surjection. So that means that gamma tilde is an open map. But it's not just a surjection, it's a bijection, right? Which implies that gamma inverse is bounded because it's an open map, right? So this is just the open mapping theorem. Okay, so now we have now we have an isomorphism. Okay, a Banach space isomorphism. Okay, so points 2 and 3. So maybe I'll leave those as an exercise because they are not so. Okay, so I'll leave 2 and 3 as an exercise. So the interesting part, of course, is the closedness, and for that you have to work a little bit. Okay, that closed subspace maps to something closed. Okay, so for 4. I'll give a proof of this because I think it's instructive. So, so it's clear. So the direction gamma inverse gamma s, this is clear, right? It's really the other direction that's hard or harder. So the direction, So let, suppose we take some point x in gamma inverse gamma s. So what does that mean? That means that there exists some, so that means that x is in gamma inverse of y, and so we have that y is equal to gamma s for some s in the big S. Okay, this is what we have. So then we have that gamma x is equal to y, which is equal to gamma s. Okay, so that means that gamma of x minus s is 0. Okay, i.e. x minus s is in B naught, which is the subspace of S. Okay. So that means that I can now write x as equal to x minus s plus s. So clearly this is in S plus S, which is equal to S. Okay, so this is really why we need to only consider these subspaces S sitting between B0 and B1. Okay, so what this proposition is telling you is something just very intuitive. I just wanted to really spell it out because it's sort of at the center of everything we're going to do from now on. Okay, it's a very simple thing, but it's at the center of everything. Okay, so the example I wanted to give you before, so this is a poor example, right? So this is a poor example, but that's still important. So let me put B0 equal to dom dmin, B1 equal to dom dmax. This will always be the setup, okay? And now I'm going to let B2 actually equal to dom dmax mod out dom dmin. And gamma is the quotient map. So why do I want to give this example? Because I really want to emphasize that the interesting information for us in terms of understanding boundary value problems is really contained in dom dmax mod out dom dmin. Okay, so all possibly closed subspaces and possibly closed, and therefore, I should say therefore, closed extensions dmin, dx, dmax can be understood as subspaces, because I don't necessarily mean closed. If it's a subspace, then it's a subspace. If it's a closed subspace, it's if and only if it's closed. Because we want to, so the question is, why do I keep putting closed in parentheses? Because the closed is the important condition. We need to know that when one is closed, this happens if and only if the other is closed. It's not just the information between the subspaces that we're interested in, that when we have one kind of subspace, we have another kind of subspace. That's really the heart of this proposition, right? So when S is closed, then gamma S is closed. When so here S is sitting between B0 and B1. Here, I should have really maybe called this S prime or something. So here, when S is a closed subspace, then gamma inverse S is a closed subspace, right? That's really important to know that. It's not enough just to know that they're subspaces, because they govern closed operators, right? So knowing when an operator is closed is really a very important question, okay? So anyway, so the point is that all closed subspaces sitting between dom dmin and dom dmax can be are equivalently closed operators sitting between between dmin and dmax, and they can be understood as possibly closed subspaces. of dom d max mod our dom. Okay, I'll write it in the next line. Dom d max mod our dom d min. Okay, so far we haven't really done anything in terms of boundary. All we've done is we've taken the problem that sees the interior and we've reduced it down to a certain quotient space, right? And the boundary stuff will come. So now let's move on to talking about boundary if there are no questions at this stage. No, doesn't look like there are questions. Okay. So now boundary. Well, understanding boundary maybe. We are only going to concentrate on the first. So the question is, are we still in the first item of what we need to formalize this? So what was the first item? This is this part, right? Desiring to have some function spaces on the boundary so we can understand closed extensions of the operator. This is all we're going to concentrate on. So item number 2 we can forget, right? Throughout this lecture, I won't really touch on item number 2. The hard... Yes, this is formalizing the first point. That is understanding boundary conditions. Yes. Okay. So now, let me just... Okay, so understanding boundary. So we're still... Okay, maybe I'll put that in. Still at 1, right? Formalizing 1. So now we have some predetermined values, okay? If we want to talk about boundary, we have some God-given spaces and some God-given maps. So we have B0, which is given as dom d min, and we have B1, which is given as dom d max. So that's fixed. But now we have another map. Let me call it gamma subscript C. So this is going to take me from C infinity C, ME, and now I'm going to have some sum of spaces. J equals 0 to m minus 1. So just m copies of C infinity C on the boundary. And this map, so this is again a God-given map if we want to really talk about boundary value problems, right? So right now it's an ansatz, but we'll see why it's the right map, right? I mean, it connects also to the problem that we first wrote out, because there we are really interested in understanding the values of the or the restriction of the normal derivative or some transversal derivative to the boundary up to order m minus 1, right? So that's precisely what this is going to be. So this is u restricted to the boundary. Restricted to the boundary all the way up to m minus 1 restricted to the boundary. Okay, so these are the God-given maps now, okay? So, I've also implicitly fixed some so T here, so where T is an inward pointing vector field on the boundary. Okay? Okay. So I have to be careful with my enumerations now. So what do we want? So in order to continue this formalization, we in light of the previous proposition, we need gamma to be defined on all of DOM D max. Okay, so that's the first technical issue that we have. We want to extend this map gamma subscript C to all of DOM D max. Okay, so that's the first thing we need. Gamma to be extended to DOM D max. Okay, because DOM D max does not just consist now of smooth functions. I mean, you can just think back to the weak derivative. So if you had partial j here, you have the weak derivative, and the weak derivative is going to consist of a lot more things than smooth maps, right? So that's the first thing. The second point here is we want the kernel of gamma to be DOM D min. But actually, that's not so bad. Once we organize gamma to be extended to all of DOM D max, the fact that the kernel of this map is DOM D min comes out of the wash, because it's really where these restriction maps up to order n-1 of derivatives are all zero on the boundary, right? So intuitively you can see that that's what the DOM D min is, right? If we consider what DOM CC was, DCC, so I mean DOM DCC was compactly supported smooth maps that don't see anything on the boundary, right? They vanish at the boundary, and D min is the closure of this as an operator, right? So we expect that DOM D min is exactly going to have the boundary traces vanishing as I've written it, right? So intuitively, this is certainly a plausible thing. So once we have 1 and 2, what we have is the following, right? So suppose I should say extended to DOM D max as a bounded surjection, right? As a bounded, well, okay. Let me not say that. Let me actually not say that, because that's a bit more of a subtle statement. Okay, so suppose 1 and 2 hold. So if I can simply define gamma on DOM D max, then what I can do is I can define the so-called check space of D. And I'm going to define this as gamma acting on DOM D max. And this is going to be, of course, some subspace of, we want it to be some subspace of measurable sections. And I'm going to topologize this, right? I'm going to topologize this space by pulling across topology of DOM D max mod out DOM D min via gamma. Okay. So what do we end up with then? We end up with gamma being a bounded surjection, as we wanted, to this space, with kernel of gamma being DOM D min. Okay, so we have our heart's desire here. So let me just say we haven't really done anything very meaningful here, right? The point is that this map gamma is really the canonical map that allows us to get from the operator on which sees the interior to the boundary. And so what we've done via this map is we've pulled across. So in the previous example I gave you, I said that understanding extension sitting between dmin and dmax is equivalent to understanding subspaces of dom dmax mod out dom dmin. So now I've just gone this extra step of taking the topology of dom dmax and dom dmin and pulling it across to h check d. So what we've done is we've pulled everything to the boundary, right? That's all we've done. But that's the first step. So once we do all of this, the next desire that we have, right? So this is the dismantling step, right? So now what we would really wish for is to describe H check D and in particular its topology from data only on partial M. Okay, so I'm going to put only in parentheses here because of course that's open to interpretation, right? Everything here is sort of more at a philosophical level than really at a rigorous mathematical level. Okay? Okay, so let's suppose that we can do that. Let's suppose that we have one to three. So this is really, I'm just pointing out a roadmap here, okay? So I want to point out the roadmap of what we want to do, and then we'll fill in the data, or we'll fill in the details as we go along. Okay. So suppose we have 1 to 3. From the abstract proposition, we have this, right? So let me just really spell it out. We have the following. So for B, some subspace of H check of D, some subspace, define dom dB. Previous proposition, precisely. So the question was, from abstract proposition, do I mean the previous one? Absolutely. So the proposition that tells us we have two Banach spaces and a third Banach space. One Banach space is the kernel of this map, for which when one of the Banach spaces, the larger Banach space, is in a surjection with the other, and then we can understand all of the quotient spaces and everything in terms of this second Banach space, right? So maybe give this proposition a name. I don't know. So I'm going to forcibly define this to be gamma inverse of this B. And so now this is a subspace of dom D max, obviously. And so this satisfies D min dB D. Okay, I think I didn't write this all that well. Let me just and then write dB of u equal to du d max u for u in dom dB. Okay, so this is what I mean. And then we have an operator now which extends d min. Okay, and the point is that dB is, oops, what happened there? dB is closed if and only if B is closed. Okay. Now let's suppose we take an extension. So if we have an extension, yes? Yes, the question is, was the action of the operator DB on you, Dmax acting on you? Precisely. Thank you. Yeah, sorry, I missed that. So now if I have some operator, an extension of dmin sitting inside Dmax, then what we have, so I can define Bx to be equal to gamma acting on Dom Dx. So this is now a subspace of this check space. Okay, and now the point is that so this is a subspace, and then point 4, the fourth point of the proposition, gives us the dBx. So if I do what I just did in the previous step and look at the operator dBx, this is precisely equal to dx, right? That's what the S equals gamma inverse of gamma of S tells us. So the point is that dx now is closed. The question was, when I define Bx, I want to define the domain of Bx precisely. Whenever I'm given a subspace in H in the check space, I define the operator by this criteria here, right? So this is the way, so this is the definition of the operator dB. Bx is a subspace now of the check space. So this is just gamma acting on Dom Dx. We're given an extension sitting between dmin and Dmax. We know that the gamma can act on all of Dmax, so in particular it can act on Dx. And then we get some subspace sitting in the check space. Now I look at dBx, which is the operator induced by this subspace, as I gave in this previous step here, where you can set B equals to Bx, and the claim is that Bx and Dx are equal, and that follows from proposition the fourth point of the proposition. Okay. So now the point is that dx is closed if and only if bx is closed. I mean, I've stressed this point before, but I just really want to stress this. Okay. So with all of that in mind, now we can actually say something a little bit more rigorous. Okay, so just to fix the language from here on, I'm going to call B a subspace of H check of D that is a closed subspace is we call a boundary condition for D. B, which is just any subspace, not necessarily closed, we call a generalized boundary condition. You can also call it a non-closed boundary condition, but then a boundary condition is a non-closed boundary condition that's closed. So maybe that's not... well, we encounter this a lot in mathematics anyway. I mean, a bounded operator is an unbounded operator that's bounded. So, okay. But, and then, of course, the associated operator. So in either of these cases, in either case, associated operator dB is just given by the domain of dB equal to gamma inverse of B, with dB of U equals to D max of U for U in DOM dB. Okay, just I've written it now and in a number of places just to really drive home the point. Okay, so let's talk about the plausibility of all of this. Okay. So as I've stated it, it's not entirely true that we can do this. Okay, so let's just study some obstacles. Yes? Okay, the question was, what is the reason that we distinguish between closed boundary conditions and non-closed or generalized boundary conditions, and why do we need to really care about this? So the point is that, as I said before, dB is closed if and only if B is closed. So often when we now move on to things like spectral theory of these operators, if you have a non-closed operator, you're not going to have a reasonable spectral theory. So what we really need to know are boundary conditions. So closed operator and boundary conditions correspond to closed operators, and closed operators are somehow the most important thing that we need to work with. However, sometimes when we're trying to get to closed operators, as we saw earlier, so the operator D subscript CC is not a closed operator. Okay, so a differential operator on compactly supported smooth sections not touching the interior is not a closed operator. So sometimes when we want to build closed operators, we have to deal with non-closed things to begin with. So then that corresponds to a generalized boundary condition if we move via this map gamma to the boundary. So it's useful to have both of these sets of language. Of course, I can take a generalized boundary condition. I mean, that's a subspace. I can take its closure, and then I get a closed subspace, so that's certainly a boundary condition. But sometimes it actually is helpful to not do that, and then to try and understand the induced operator, and then maybe show it's closed later on. Okay, so and that really comes down to concerns with questions about the regularity of sections of operators corresponding to certain boundary conditions. Does that answer the question? Okay, great, thanks. Okay, so let me just really try and get through what the obstacles might be. So the obstacle for number one, okay, so the formalization, okay, or, well, actually, let's see. No, this is number I. Sorry, I mixed up the numbers. So this is number I, which is here. All right, so we want to define gamma to be extended on the whole of DOM Dmax. Okay, so so what might be a problem here? So let's look at this cylinder. So let's take N to be well, a compact manifold. Well, actually, let's make it really simple. Let's take N to be S1, in fact, right? And let me take M to be equal to 0, 1, non-inclusive cross S1. Okay, and so my G is equal to just the line segment plus just the usual metric on S1. So if I draw this, I have, oops, can't draw straight. Okay, so that's okay, yeah, so that's S1, and this corresponds to 1, and this, so this is 1 cross S1, and this is 0 cross S1. Okay? So this is now a manifold with boundary. But the boundary of this, so via our definition, the boundary of this is simply S0 cross S1. Okay? Now let's just stick to first order because that makes it easier. So let's just consider the Hodge Laplacian on here, or the Hodge, not the Hodge Laplacian, the Hodge Dirac operator. So this is just d plus d dagger of g. So then the gamma is just going to be the map u restricted to the boundary, okay, as we wrote it out before, right? Because, well, m is equal to 1 here, and so m minus 1 is 0, so we only have the 0th contribution, right? But here we absolutely cannot have dom d max being a surjection to just the trace on one end, okay, the boundary trace on just 0 cross S1. We actually really need to consider u restricted to both, sorry, S1 cross both 0 and 1. Okay, so intuitively here we can see that the boundary really should be the piece 1 cross S1 as well as 0 cross S1, right? So why do we include this, why do we talk about this notion of a manifold with boundary in this way if, you know, in this picture it doesn't really agree with what we're seeing in the picture? Well, the point is that in geometry, you know, the metrics you get might not be just the ones that are induced in some embedded way or some particular way. So you could turn this into something by allowing the piece at 1 cross S1 to head out to infinity, right? If we scale the metric in a way that as we head out to 1 cross S1, the boundary gets pushed out to infinity, then indeed we only pick up the boundary at 0 cross S1. Okay, so then you could argue and say, well, maybe we should define the boundary to be just the boundary that we get of this as a metric space if we just consider the interior, and then we take the closure and then consider that as a set. Of course, we could also do that, but you know, we wanted to stay in this sort of intrinsic geometric way, and this is why we did things the way that we did things. But then we get this kind of we could potentially come across these kind of problems, right? But this is not really a problem, because this is really saying, I mean, if we're now considering 1 cross S1 as a part at infinity, we're really saying that we're not really controlling the operator in a reasonable way at infinity. Okay, so how do we really get around this? Well, we really need a fundamental assumption here, right? So the question is it obvious that we shouldn't have, we cannot have such a surjection? Well, yes, because I could consider compactly supported smooth sections that go all the way up to that take some value at 1 cross S1, right? Meaning that they don't go to 0 at 1 cross S1. Okay, so consider a section on here which is constant, say. If I do that, what will happen now when I look at the dom d max only restricting to this part of the boundary, if I look at dom d max, I can show that such sections, because I'm integrating against things, so in the construction of dom d max, I'm only looking at things which are compactly supported on the inside part. So such a section will be in DOM D max, and then I'm trying to control it only from the value of 0 cross S1 without really considering the values at 1 cross S1. Okay, so maybe I need to write. Well, of course, here, if I define my boundary to include the piece 1 cross S1, then it's certainly true. And that's why I'm saying that we need to consider U restricted to both S1 at 0 and S1 at 1. So if we did that, then we wouldn't have this problem. The point is that we've defined this manifold to only have a boundary piece as 0, according to the definition, our definition of a manifold with boundary. And we have a certain singularity or incompleteness at 1 cross S1. Okay, so let me write down a condition that allows us to get around this, which is not satisfied here, right? We want to say that C infinity C of, if we assume that C infinity C is dense in DOM D max, then we're okay, right? If we have this, then we're okay. Clearly, C infinity C M of E is not going to be dense in D max here, because we have this piece here and we can never reach this piece, right? So, I mean, here we're really looking at sections which are supported, say, here. But it's always going to be 0 here, right? But we could have sections in D max. When we formulate D max, remember D max. So this operator is a formally self-adjoint operator. So D max is going to be just the Hodge restricted to, okay, I'll write CC adjoint, right? So we're really looking at sections that can take a value here, that can take a constant value here, because when we integrate, we're integrating against things that are only supported on the interior. So the fundamental condition is this density condition, and sometimes this is called the completeness of the operator. Okay, so we need the operator to be complete at infinity. So, okay. So I'll maybe leave an exercise here. If M is compact with boundary, then A1 is satisfied. Okay, so the way that this assumption comes in will become clear in time. Okay, so I won't labor the point too much. So the second point was the kernel of the gamma being equal. Yes? Question? Yes? Mm-hmm. Yes? That's right. So the question was, if instead of 0 to 1, we had 0 to infinity, then certainly that's true. Then we would have the boundary only being 0 cross S1. Because somehow the boundary is then sitting at infinity. Of course, we could also keep 0 cross. The topology of the two things are the same, and in fact we could do that to 0, 1 here also, right? But then we have to include the information about infinity in the dt part, and we have to push 1 out to infinity. And if we did that, we would also have that that this is dense in DOM D max, because we have of course a diffeomorphism between 0 to infinity cross S1. Yes. There is a difference because here we're really looking at the induced metric in the embedding. If we pulled back the metric across the diffeomorphism, then the dt part gets pushed out to infinity, right? So, okay, so the kernel being dom d min, so this follows and needs typically the condition A1, okay? In the when we go into the non-compact setting. In the compact setting, A1 is automatically satisfied. The third condition, if I recall, was to describe, so this was to describe the check space purely in terms of information on the boundary. So I have to wriggle and lie a little. So this is possible to a large extent. Okay, so I don't want to give away all of the secrets right now. These loose notions we will see in a very concrete and a rigorous way as we move along in the course. So what it means for this to be possible to a large extent and so on and so forth, we will move along, we will see as we move along in the course. So let me just think in terms, so in order to further describe these things, we need to really talk about Sobolev spaces, and I'll start talking about Sobolev spaces maybe next time. There was maybe maybe I'll just, at this point, I'll give a very quick additional example just in terms of this density result, right? So let's just suppose, so this is an important theorem just to understand what this density really means, right? Suppose that M has no boundary. So suppose M, well, Mg is Riemannian, and the boundary of M is empty. Then it's a very important result of Chernoff's. So suppose that the principal symbol, so and this is a particular case of a theorem of Chernoff. So if so D is first order, so we need to assume that D is a symmetric first order operator, right? So this is diff 1 E back into itself, symmetric, i.e. DCC UV, so DCC formal adjoint is itself. And so in this case, so the boundaryless case, I should just say that in this case, C infinity CC is equal to C infinity C. Okay? It's a symmetric operator, so symmetric. Yes. The notion of it, so the question was, is symmetric what we call formally self-adjoint? Formally self-adjoint. So in general in the literature, what you have is symmetric, because formally self-adjoint really is a symmetric operator with domain compactly supported smooth sections. Symmetric in general, if you're given two operators, D, or one operator, D, symmetric means that on the domain of that operator, the symmetry relation holds. Okay? So formally self-adjoint is particular language in geometry when we talk about compactly supported smooth sections as being the domain of the operator. Okay. So we also need to know that the principal symbol of this operator, so this is a particular case, is bounded in terms of psi of G. Okay, so this is the operator norm. So in this case, a consequence of Chernoff's theorem is that D to the power of K, okay, so he says D to the power of K is essentially self-adjoint. Okay, so this is also something you will encounter when you read some geometric literature. So essentially self-adjoint is actually the same thing as saying that the closure of the operator is self-adjoint. Right? So it's equivalently that, right? That's really the definition of it. So DCC, I should say. Okay? So in our language, what does that mean? In our language, so we have DCC of K is a differential operator of order K now. It's again symmetric, that's not hard to verify, but what it's saying when we say that it is self-adjoint is actually that DOM D max, dk max, mod our DOM dk min is 0. Okay? If you're essentially self-adjoint, that's what it means. So, the main thing here, okay, I should say, sorry, complete Riemannian. That was the point of all of this. And that's why the choice of language to say that the density of this in DOM D max means really that the operator is complete. This notation really comes from the geometric setting, the boundaryless geometric setting, when you have a complete metric and you have some control over the principal symbol of the operator in terms of the metric. Okay, I should say there's a constant, right? So there exists a constant. So this really means that, and this is g at x, sorry. So this is really saying that the completeness of the metric really gives you a sense of completeness of the operator. Okay, so the closure being self-adjoint, that's really saying that compactly supported smooth sections is dense in domain D max. Right? That's what this quotient is really telling us in the boundaryless situation. So anyway, sorry, I didn't really prepare to talk about this correspondence between complete metrics and complete operators, but that's really where the language comes from. So I will leave it at that, and on Wednesday we will start talking about Sobolev spaces, because that's necessary to really define, to actualize our goal number one, which is to define gamma on all of DOM D max. Okay, thank you very much. Any questions? Yes, sure. Mm-hmm. Yes. And df is the psi, yeah? df is at x psi, yeah? Okay, so the question was, why do we have f to the power of m when we define the principal symbol for an operator of order m? So it's, yeah, I mean, in some sense you can write out the operator as a sum of you know, inside a chart maybe of these different orders. So it's not exactly a Taylor expansion, but it is, of course, an expansion of just how you write the operator with the coefficients. And the whole idea is that, of course, you want to extract out I mean, the principal symbol has a certain homogeneity. And the f to the m means that it allows you to, you know, kill all of the terms that are beneath order m, so you can recover just the mth order term. Because that's what survives when you differentiate this m times, right? So I mean, the point is that if you differentiate it less than m times, then you still have a term of some power, some f sitting out the front, and when we evaluate that at 0, that term disappears. So the only term that survives is the term of order m, because that gets eaten up when we differentiate, and that's more or less the intuition. Yes. Okay, so that's an interesting question. So the question was, can you write this recursively? So the lower order symbols for an mth order differential operator are not so well behaved. I mean, certainly, that doesn't give us somehow an invariant section, and this ties in with symbol calculus if you get into pseudo differential operators, and these things can transform in a not so nice way under coordinate transforms when you're beneath the top order of the operator, and that's why it's difficult to get something like this for the lower order things. But of course, if you're inside some sort of a trivialization, you could try and do this sort of stuff and understand what the full symbol looks like, right? Yeah. The formal adjoint. Yes, that's exactly in the formal adjoint, yes. Yes. Yeah, actually, I mean, so the question is, why is the transpose popping up, or why is it just the transpose that I'm writing in the formal adjoint calculation? So that's maybe a little detail that I sort of swept under the rug. The point was that the homomorphism that is really defined using orthonormal frames for the metrics H, E, and HF. So that is the transpose in those orthonormal frames. So that's a transpose in the good sense of the transpose we understand in Euclidean space. But of course, that's because we're using orthonormal frames, right? So if you unravel that, then that has to really be the adjoint with respect to the metrics. Yeah. So I just hit that just to make the calculations easier. I swept that into the matrix itself by doing everything in an orthonormal frame. Yeah. Okay, so see you on Wednesday then.